Hello everyone, it's April 23rd. Today is the day I'm leaving, so I'll leave tonight. The flight is 11 p.m. That's quite late. But the good thing is tomorrow I'll arrive in Fort Lauderdale 7:30 in the a.m. So it's good. It's like just spend a night on the airplane. And tomorrow I have the entire Sunday left to do, to work or whatever. So let's first start to do today's challenge, which is encode and decode tiny URL. I have done this before. Look, I downloaded it. What the hell? When did I do it? Back in March last year. Ooh, I downloaded it. Okay, why did I download it? Why did I download it? Huh. Did I give it a reason? I don't remember. Alright, tiny URL is a URL shortening service where you enter a URL. Hold on, let me put it in the right position on my laptop. Okay. And such as this, and they will return a tiny URL. Design a class to encode and decode a tiny URL. There's no restriction on how you encode or decode. You should need to ensure. Hold on. Oh. Alright. You should encode and decode with anything, right? Any type of algorithm. You need to ensure that URL can be encoded to a tiny URL, and then tiny can be decoded to the original one. So given the long, you return a short. Huh? Decode returns the original long for the given short. Wait, hold on. Hold on. Hold on. That will pass. Oh, my bad. There's no long, it's short. This will pass. Yeah, what the hell? Is that how it was last time? I don't know. Yeah. Look, this is a year ago, a year and 1 month ago. I did exactly the same thing that I did today. All right, so I don't know. I don't know how to proceed, man. So okay, let's think about it, right? We're gonna shrink it, right? We're gonna shrink it. So basically, it's I don't know. We have to find an algorithm that shrinks. Basically, given a string, we want to shrink it, and it has to be unique, right? Uniquely shrink it. Oh, is this where the robbing carp comes into play? The robbing carp is dealing with a pattern. I mean, robbing carp will have is a hashing function for a string, but if I remember right, is If the hash value is not the same, then they're definitely not the same. But if the hash values are the same, they can still be collision. So I don't know, like, what are a good way to shrink? Well, I mean, repeated value can be shrunk, right? So we can have a rule. If we have consecutive values, then we can shrink them to the value and a number, right? So it should be a value and a number, value and a number. But if it's an individual character, then we just do that, right? And we can remove, let's say, the input. It's just basically asking how do you create a hash function for a string. Well, how can we call it hash? Oh shoot! Sorry, I forgot to do this yesterday. Let's see. A hash function, right? So, yep. Hash is not defined. Wait, I'm gonna call this called hash. Oh, okay. Maybe. I don't know. So what do we say? Let's try that. It's like I don't want to write my own hash function because it just sounds silly, right? So what do? We copy and then we paste. Okay. All right, so what we're gonna do, initiate self dot hash map equals this. And every time we come, we just say self dot hash map long URL dot hash equals longer URL. Now return H, and then this will just return self dot hash map short URL. Let's see, this one works. It works. It works. Yeah, I know I don't like this question. Oh my god. I don't like it because basically it's asking you how to do a hash. Use two dictionaries. Oh, we can generate a random string. Yeah, we can generate a random string. Hold on. That give me an idea. From random return or import choice, right? So we just that choice, dude. So what we can do is hold on. I have a couple of things to check. Oh shit. All right. So string dot. Wait, you have to import. Yes. Letters. No, 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 no. This is good. What else do we have? Digits. All right, can we do this plus string dot letters? Yes, so we're gonna choose that, right? Still do this. So in code, we're gonna say while true, okay? And then hash, not gonna be hash. We say how many digits? 32. How about 32? So we just say for this range 32. Say this dot join choice self dot basis. Oh, do I have to import string? Okay. So we copy this thing. So it's gonna be these two. Okay. And then there'll be choice self dot basis. All right. So we do that. We'll get an h, and we say if h not in self dot hash map. Self dot hash map h equals long URL. Then break. Now, don't break. Return h. If it's in, just do another one, right? So we do that, and decode is the same. So encode is a random 32-bit. Let's see how fast. So this is just for each long URL, generate a random string of any size. Now to avoid too many collisions, actually we can say like how long, how much we can do just by checking out the size of the string. 10 to the 4th. 10 to the 4th I can do with 2 to the 10, right? 2 to the 10 is 1024. No, that's 10 to the 3rd. All right. So 11, 12. How about just 16? That's just 16. We set the random string have 16, have size of 16. Maybe this is what they're looking for. Yep. Yeah, I think this is the standard solution. Okay, okie dokie. So let's see. Ha! Ha! Oh, God. This is so cool. This is so cool. Oh, this is my idea. This is my idea, but it's a little bit better because if you look at it, it has two things. Ah, this is good. Range 6. 6 is enough? Oh, yeah. Why you have to... No, it's... We have so many. Each position has 36. Right? No, the 26 sometimes has 10. You only need the 6 to encode. Yeah. I was not calculating well, but this is... Yeah. So I did, yeah. I'm proud of myself. This is a. Yeah, I did that too. Yep. So update. Now my idea is the same as Mr. Pockman, but he pointed out that using just one dictionary leads to the same long URL getting hashed to different values if it is encoded more than once. Thus, we need another dictionary to keep track of the hash for each long URL. So in this case, and also my calculation for the length, right, of the tiny URL is not correct. since for each position in the tiny URL, have 26 times 2 plus 10 equals 36 different options. A size of 6 leads to 36 to the power of 6. Right? No. Oh, yes. 36 to the power of 6 different ways. This is more than enough for the problem. So we're going to go down to 6, and we have, we can call it URL to hash. We can say long to short and short to long. Okay. So long to short, and then short to long. Okay. And then if long URL not in long self dot long to short, then we do this, and then we return self dot long to short long, right? And then, well, true, we do blah, and then we say if h is not in self dot short to long, and then we say short to long and self dot long to short. So long equals h. Don't do this, but we do break. Okay, and then this is just going to be short to long, short. All right, try this. Yeah. This is good. I like it. All right, okie dokie. That's that. Today's challenge. Yeah, I have to be like really careful for the remaining of the week. I think I don't have of the month. I don't think I have another time travel. So I have to be very careful. Anyway, so I'm done with this. So how long have we been doing? We have been doing this for 23 minutes. So let's do a few more problems just for fun. So this is 235. Add two integers. Oh, you gotta be kidding me. What the heck? What the heck? You serious? You serious? Lack of effort when putting together this problem. This is barely. At least say find the sum of a list of numbers, right? Oh, it's a zero line. Oh, oh, cold golf. Wait, maybe it's asking for like integers huge. Wait, how big is integers? 100. Oh God. Oh, that's yeah, that's pretty smart. Yeah, this is actually pretty smart. This is actually pretty smart. Hmm. All right, so that's that. All right, let's try this. This one will be more serious. Maximize number of subsequences in the string. You're given a zero index string and another zero index string pattern. Oh no, pattern, pattern. This is one of the application. I remember this is one of the application of the, you know, either the Z algorithm or the KMP. Of course, go for Z algorithm. It's easier to implement. Okay, add either pattern 0 or pattern 1. Hold on, you can add either pattern 3, 3. The hell is 3? Pattern 0 or pattern 1 anywhere in text exactly once. Note that the character can be added even at the beginning or at the end of the text. So we add a pattern, right? And now we try to find maximum number of times pattern can occur as a subsequence of the modified text. So you can either add, hold on. So the pattern, oh, that's slightly different. The pattern is only 2. The pattern is only of length 2. So we can add either A or C to either ends in between text. Wait, hold on. You can add either this anywhere in text. My bad. Anywhere in the text, exactly once. So we can add this text anywhere in it, and once we got it, we get another number of time AC occurs as a subsequence is A, C, A, C, and A, C. That's 4. Yeah, because we have 2 C's and a 1 A. If we add a C, that will only give us 3. If we add a C at the beginning, that will only give us 2. If we add an A at the end, that's only 2. If I add an A in here, that will be 1, 2, and 3. This is good. Alright, so it's not KMP, nor is it Z algorithm. Okay, so we count. Because there are only 2, so we count the number of the first and number of the second, right? The entire thing. And after counting, okay, after counting, we say we have the first one, right? And so we'll have a total number. How do we find the number, total number? Well, we find, actually, let me think about this. We have 2 arrays. The first one is the indices of the first letter. The second one is indices of the second letter. Okay, so we have that, and we put them into a queue. So that doesn't matter. So the first one, we'll check which one is smaller, right? Then we can get. So let's say first one is smaller than the first of this, then the entire thing we can include, right? So we have that. And then once it's done, we will just ignore that and go to this next one. When I go to the next one, then in the bottom, we're just gonna go see, oh, if it's larger, so boom, so we hit something that's smaller, then we'll check it again, right? And then move to the third one, and then we'll go, this will also go, right? And then we'll keep going, okay? Oh, eventually we'll end. Okay, that's how we're gonna count a number of different ways. But now we say we want to add a value. So we want to add, definitely the best way to add is, if you think about it, if the starting one, the first letter is smaller than the second letter, right? Then, in that case, we shall add, no. All we want to do is we can add a value, right? So it can make every single time when the first one is trying to do, and then we just add one, then we can add that many more, right? Think about it. Think about it. If we add the first letter, right? You add at the end, useless, right? You add in the middle, so you only have to increase that amount, right? So you want to add it at the very beginning. So that's one solution. We add the first letter to the very beginning. Then we can have the entire thing, right? We just add that. So that's one option.
Second option, right? Second option is if we want to add a second letter. Now, if we want to add a second letter, we want to add it to the end, right? Because when we add to the end, then every single time the first letter is going, then we will have one more, right? We'll have one more. So, in that case, what we shall do is first find out, we need to first find out the total, yeah, we're going to find out a few things. Find out a few things. So first of all, I want to have two arrays. So P1 index P0I and P1 IDs. P1 IDs. Okay. And then for T in text in this T in enumerate text, if T is equal to pattern 0, then P0 ID start append if T is equal to pattern 1, P1 ID start append right? So blah 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 towards the end. And then we need to find out the total number, so we call the result equals 0. And then we have I and j. Okay, I equals to j equals to 0. And I say while I is smaller to len p0 this and j and yeah, or j is smaller than len p1 IDs, right? And then we say if P0 IDs I is smaller than P1 IDs j, right? In that case, rest plus equal to, right? Plus equal to len P1 IDs minus j. All right, let's see if this is correct. So I have 0, 1, 2, right? And then that's 3 minus 1 is 2. Yeah, that's correct. There are 2. Right? Len minus this. So that's the total number, including, right? Including this. So, okay, so if that's the case, ooh. All right, so if I is madre mia, let's do this. M and hi, that's M, that's N. All right, we say if I smaller than M, right? Then we say if I smaller than M and if J is equal to N or this, then we do that, right? After that, we say I plus equal 1, and then J doesn't change. Else, no. If this is elif, P0 this I larger than P1 IDs. Oh, that should be the only one, which is J is smaller than N, and so I can just do else. Okay, else. All right, else is this one is larger than this, then J plus equal 1. So what I think is I don't need to consider J, I only need to consider I. Alright, so this is not necessary, so we'll just do like this. Alright, I just kept incrementing until the end, and then we will have the total count. Now, we shall return res plus maximum of m and n. That's what I think. Check it out. This one shall be 4. This one shall be 6. All right, text, pattern, maximum text, pattern. Yep. I think this one is good. Edge case, let's check the edge case. Let's say text.length, A, AB. Okay. We have it like a 0. Text length, AB, this shall be a 0. Yep. I think this is it. Oh no! What the heck? That was ridiculous. I was so wrong. What? Expected 496? Wait. What the hell? Wow, this is in a contest. I will be so wrong. I'll be pissed. 496? What? Oh. The twos are the same. Screw me. Screw me. The two are the same. My God. So the twos are the same. Which means, oh, let's see what happened here. So I think one of them is empty. Yep, one of them is empty. My bad. I did not. Okay, this is an edge case that I did not. This is not even an edge case. So if the two are different, we got it. If the two are the same, we've not got it. Okay, so they're the same now. So they're the same. So what we have is the first one, the rest the second one, the rest the third one, the rest. So it's going to be 1 plus 2 plus all the way plus to 31. And, oh, that's 32, right? So we say, blah, blah, blah. We say if n is equal to 0, right? So this is the pattern, the two letters in the pattern are the same, right? Then we simply return m plus 1, right? And then plus 1. times n plus 1 divided by 2. No, that will be 32, right? 32. Wait, hold on. Let me think again. So the pattern wise, I have, so it's only, so if I have m numbers, right, the maximum we can get is n minus 1. So if I have n plus 1, the maximum we get is n. So no, this is not right. So times m. That is correct. All right, so we need to add this line. Yep. So my bad. I did not pay attention to this. All right, let's try this one. Ooh, what the heck? Too wrong. Now this is a logic issue. Something is not right. The hell? Hold on, let's see. Print P0 ID, P1 IDs. Oh. My bad. Yeah, because it could. Oh my God, how could I? Now, if this really happens in a contest, I'll be pissed. I'll be pissed beyond your imagination. I'll be so pissed. There are many ways to check. I picked the wrong way to check. You gotta be kidding me. You gotta be kidding me. Come on. You gotta be kidding me. So, how should I say it? Too confident. Now, the edge case is when pattern 0 is equal to pattern 1. But it is important that to check that this is the only way, right? That this is the only legit way to check for the edge case. If we check n equal to 0, that is wrong. ON, because this is ON, and this is ON plus this n plus n, which will be smaller than n. So overall is ON. Yeah, I don't know why I would not take into consideration that. All right, so this is straightforward. So to see if it's equal to this, count. Count. So basically, we're trying to think of this one going backwards. And going backwards is exactly the same as going forward. Going forward, we have the recorded, and then we're going to check the indices. But now the counting is, if we count this, right, and we need to return. So if it's equal to pattern 1, right, if it's equal to pattern 1, which is the end, then we need to know the number of count count 1. Hold on, let me think again. So what we're saying is if we have the current character is equal to pattern 1 and resolve what you say. If I have 2 pattern 1, I will add pattern 1. Oh, count 1 is 0. Man, you should say count 0 instead of count 1. So that's the total number of count of zeros you have, right? Because if I end up here and I have 2 counts that's in front of, then okay, that makes sense. And then if I found a pattern this, then we say we're starting from this is we don't have anything because that's a new thing, right? But if we find pattern 1, then we can do this. Okay, now at the end, and then we yes, that's good. I'm gonna do this one. One pass. Exactly k times. Then, if we can add a k times, so again, think about a bunch of this, right? We add a 1 time, we add this, we try to add at the front, and then we can have the entire of this. But let's say we can add can add multiple times either character in text. So it's the same, we cannot add both. So it's the same text, we add multiple times. So we add in the front, right? We can add at the back. Then shouldn't we just keep adding? Right? We just keep adding, which would just be this times, right? This times. But it'll be more interesting if you can add either one. Well, I think this is what it's trying to say. You can add either character, not exactly one. You can add 1 here, 1 here, 1 here, 1 here. Something like that. That would be fun to think about. Yeah, and now we say we can add this. Then we get a total of this. So we should be 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. Right? Yeah, I think it's just we find the maximum of the 2, we add 1. Find the maximum of the 2, we add 1. Find the maximum of the 2, we add 1. So that will be my solution. Alright, so we're going to go solution 2. It's the same idea, but much better. This is from 215. Similar idea, but much better implementation. And without the need of extra arrays to keep track of the indices. Only need to keep track of the count of pattern 0 and pattern 1, right? We'll just keep counting of that, and each time pattern 0 is encountered, we can produce 0 new patterns. But each time pattern 1 is encountered, we can produce count 0, right? Produce the current count 0 number of new patterns. So I'm going to say count 0 and count 1, right? Both is 0. And of course, the result is this as well. And in this case, we can just do for t in text, right? we say if t is equal to pattern 0, then count 0 plus equal 1. If t is to this, then rest plus equal to count 0 because we added a new count 1, right? We added a new 1. So, yeah, so we encountered a new one, then all the previous count 0 can match with that. So we do that and then count 1 plus equal 1. And blah, 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 blah. At the end, then we're just going to return result and then maximum count 0 and then count 1. All right, let's try solution 2. How did he deal with this situation? Man, I don't think he had any, wait, did you check edge cases? Oh, shoot. If it's equal to this count, and then it's not elif. Notice the trick here. It is not else if. This is to handle the case where pattern 0 is equal to pattern 1. Alright, if they're equal, then we count pattern 0. You have to count pattern 1 as well. I don't understand. What the hell? If it's equal to pattern 0, the pattern 0 we just increment, and then if equal to pattern 1, then pattern 0. You know what? This if I increment count 0 first, and then result plus equal to, it's a bigger one, right? Because we were thinking every time we encounter, if we first check if it's pattern 1, if it's pattern 1, then that's a new thing we encounter pattern 1. So everything we have so far, right? If we do pattern 0 first, then pattern 0 grows, and then we do the same thing, and then we count pattern 0 again. Oh my god, this is so good. Also notice that the check for pattern 1 must occur before the check for pattern 0. Madre mia. Otherwise, we will double count. We would double count when pattern 0 is equal to pattern 1. Okay, that shall be it. We've done it 1 hour. Perfect. All right, so that will be it for today. I will see you guys tomorrow back in Florida. Adios.